Hello, everyone. Thank you for tuning into this presentation. We are still currently awaiting our speaker, Ezra. So you guys want to bear with us. We will give him a little bit more time to make an appearance. Thank you all. As I say that, I believe I see him down in the chat. Ezra, you should be able to pull up your video. I will confirm that right now. There, I just allowed you to come on, I think.
Hey guys, can you hear me all right?
Yep, we got you.
Okay, sorry I'm late. The internet where I am is not great.
No worries. Go ahead.
Yeah, I appreciate it. So let me just pull up my my tab here.
Apologies, Ezra. You might have to unmute and undo video. I accidentally hid you from the screen.
Hey, okay, sorry about that. You all can hear me all right?
Gotcha.
Okay,
Thank you.
excellent. So yeah, I do want to be mindful of time here. I know I'm running a little bit behind, but I wanted to talk to you today about development framework for autonomous naval operations, and more than that, we think that the tools that we provide are really going to help expedite the development of all-domain operations, and particularly autonomous all-domain operations. So a little bit about our company. Applied Intuition provides software tools for autonomous vehicle development. We're about 5 years old now. We're a Series D company. We're venture capital backed, and 250 right now. We're on track to grow by a couple more over the next couple months. We're based out of Silicon Valley, but we've got offices all around the U.S. Our newest one is in D.C., and also all around the globe. We draw primarily from Google, Waymo, Apple. So really, we look for the best software engineers and also the best autonomy engineers. We currently support 17 of the 20 large auto manufacturers globally. So some of our public ones are Toyota, Ford, VW, really anyone but Tesla. They do a lot of their stuff in-house. So chances are, if you are driving a car that uses advanced driving systems, those were built using our tools. So we'll get right into the problem as we see it and the solution that we provide. So all-domain operations or distributed maritime operations, multi-domain ops, I'll just shorten it to all-domain operations here. It's really about many things, obviously being able to operate in air, sea, sky, space, have comms links between all those domains. But more than that, especially given the near peer or peer competition we're facing, we know we need, and this is recognized across the services, we need to get away from exquisite platforms and transition to attritable things instead of exquisite platforms. Autonomous vehicles, or UXVs, we'll just shorten it to UXV for this conversation, are key to that. They're key to attributable systems and also to ADO. They enable ISR. They can help augment human decision making. They can really help close the kill chain faster. So across the gamut of ADO, autonomous vehicles are critical. There are a couple of obstacles, though, to efficiently maturing UXVs within and across domains. So just a couple of them, rattling them off from the Navy perspective. So resource constraints is one of them. The Navy cannot test all vehicles in a real-world environment at all times. It's expensive. It takes people out of training environments and out of garrison. So it's impossible to train as much as you would like in a real-world environment. When the Navy does go to the field, there's a huge scope of problems that need to be solved with UXVs. So, a couple of them are waiting for the right weather conditions, solving hardware issues, doing comm exercises. So a lot of time is spent doing things other than testing how the actual algorithms and the things that power the autonomous vehicles, testing the strength of those. So the actual autonomy algorithms is what we focus on, right? Autonomy is a software first problem. And so we think that the right answer to do a lot of the testing and maturation of autonomy algorithms is simulation. And not just any simulation. There's AFSIM. There's a couple of other government-owned solutions. But we see the right solution as being really predicated on autonomy. So architected the right way for integrating autonomy and testing autonomy in an environment that's of sufficient fidelity. So the simulation that we provide, and you can see a preview over on the right side there, we'll get a little bit more into that in a couple of slides, is this high fidelity physics-based world that lets you test out your algorithms and see really across your full AV stack how your algorithms are going to perform. So we think that lets you, of course, test your algorithms. The other piece that's really important is validating ConOps in a cost-effective way that minimizes cost and operational risk. So we'll get some more into our actual tools. Before that, though, just wanted to give a really brief overview of what an autonomy stack looks like. So the modern autonomy stack is modular, and it's based on the OODA loop. So we, on the commercial side, we call it sense, perceive, decide, actuate, but it's really the OODA loop, right? So on the sensing side, or the perceive, or the observe side, we've got sensors, right? So sensors from radar, LiDAR, EO, IR are actually picking up what's going on in the outside world, and they're taking that raw data and they're passing it over to the orient side or the perceive side. So certain sensors provide localization capabilities, answering the question, where is the vehicle? Others, like EO and LiDAR, answer the question, what is out there? What can we see? That all gets fused together and passed over to the deciding part of the stack. So that's prediction and planning. So based on the inputs, based on the actors or the obstacles that are perceived, what should the stack do? What should the vehicle do? And where should it go? Right. So that's the prediction part and the planning part. And the last part of it, closing the kill chain, is acting. So actually turning those outputs of here's the decision we should make. We should go left. We should go right. Into controls. So deciding how much to turn the steering wheel, deciding how to orient the drone, whatever it may be. So from the simulation perspective, what that means is there's two relevant simulation components. One exists on the perception side, and so we call it sensor level simulation. So it's simulating what the actual sensors are seeing, and so that's relevant for the perception module, because the perception module is the one deciding, is that an enemy, is that a friendly, is that an obstacle that I can get around, other conditions that are relevant to the actual seeing part of things. So we call that sensor sim. That's the first part of a stack. Once you close the loop and pass that over to the deciding part, that simulation looks like, all right, sensor fusion has occurred. We've seen this thing. It's a bus or it's a military vehicle. So that's the object, right? So we call that our object level simulation. And so that is in a post-perception environment. What actions should the UXV take? So getting into the sensor level simulation that we have, this is, again, a high fidelity, physically rendered environment for test and perception systems. So on the open loop side, that means really just focusing on the perception module. What is it seeing? And then closed loop, given what the perception module is seeing, what action should it take? So a couple of things to call out here. On the left, you can see this high fidelity water-based environment that we created. This is for security towers based on a Fort Benning environment. So you can see a simulated jet ski moving left to right across the screen. That's the target, right, that we're trying to track. So what you use this for is seeing, does your perception stack pick up on an obstacle or on an adversary? Does it label it the right way? And then does it actually track it correctly? We could also see, if you look at the screen, if you look at that left image, you can see that the screen is slightly occluded by rain. So we can also model weather events with a lot of fidelity. So that allows you to see in different conditions, whether that's rain, snow, dust, does the occlusion or does the blockage on the sensor affect the algorithm's ability to actually pick up on things and do what it's supposed to. So again, a big part of, or a big obstacle to real world testing is less than ideal conditions. This lets you see how your perception stack will perform in those conditions. On the right side, you see a simulated aerial environment. So this is a drone in a Western Ukrainian environment that we created to see a couple of things. One, based on this ontology, is the stack able to see what these are and label them correctly? And then also, as you cycle through sensor types, do all sensors perform the way that they're supposed to? So the way that we actually build our synthetic environment, because it is physically rendered, things reflect light the way that they would in the real world. So what that means for toggling sensors is that regardless of the sensor type, you can see light reflecting off of those materials or off of those objects the same way that they would in the real world. We also model in heat, so you can see on the IR sensor that heat is being modeled. And there's also meaning ascribed to every pixel. And so that means you could do things like segmentation. The last thing I'll mention here is our simulation comes with ground truth, so annotated labels. As you test your perception models, you can see whether the annotations that the perception model is ascribing match up to the perfect fire annotations that are created in the simulation. So we provide simulation for EO, IR, radar, LiDAR, and synthetic aperture radar, really across the spectrum of common military use cases. We're working on ELINT and some more, but I think we cover the basic suite as it exists now. All right, so I know I'm running short on time here, so I'm just going to expedite this a little bit. Cole, I've got until 3:30, right?
Yep, 3:30.
Okay, great. So I'll just cover this object level sim quickly. So this is, again, that post-perception environment. This allows you to see both single ego, so single UXV, and multi-ego collaboration. So this essentially takes the planning, prediction, and control aspect of a stack and lets you see, given a certain scenario, how will that perform. So in this example you can see here, we're seeing a bunch of different egos interacting and responding to a swarm. So this is what we see as really valuable for mission set creation and testing. You can, a user on the Navy side can create missions really easily, just a drag and drop graphical user interface, and then test their ego's performance against it. So this is essential for not just seeing how your stack will perform, but also for seeing how UXVs will interact with each other. So from a multi-domain perspective, how will the drone in the sky and the drone in the water and the drone on the ground, potentially, obviously less relevant for Navy, but how will they all interact with each other? Is it in a way that enables, say, cross-platform slew to queue, or is it in a way that that doesn't necessarily foster collaboration? And so for the Navy use cases, as they're bringing aboard a bunch of different vendors with a bunch of different capabilities and different proprietary algorithms, this lets you test out your integration ahead of time. So it doesn't solve the entire end-to-end. There's still things that need to be done in the real world. But this lets you see, at least based on the software side of things, whether the stacks are compatible. So got 3 minutes here. I do just want to kind of sum up what the value proposition is. So we see the object level and sensor level simulation together as being really powerful, a really powerful way of advancing all domain operations. So simulation is the most efficient way to train while resource constrained. We started out with and have been very successful on the commercial side. It's a pretty commonly accepted commercial best practice to do a lot of testing in simulation. And these are big companies with big budgets, but at the end of the day, there's only so many hours in the day, and there's only so much money that you can spend testing things out in the real world. So simulation really lets you test out those edge cases, those mission sets that would just be really time consuming to test out in the real world. The last thing I'll mention there is that taking advantage of high performance computing, you can run thousands of scenarios in the span of a couple of hours. Things that would otherwise take weeks or months to test out, you can test out in a much shorter time period. You can also parameterize the simulation, and what that means in kind of colloquial is you can combine every possible scenario, so every combination of weather, speeds, number of assets, and run those all against each other. So what you're walking away with is a much broader idea of your autonomous vehicle's capabilities than if you just tested it out, say, 10 times. So for the Navy, this simulation provides a test bed for evaluating autonomous platform maturity. So answering the question, is this UXV actually ready to go to real world testing before you do it? Often the answer is no. There's a lot more actual algorithm work required. The second is simulation provides you a sandbox for really maturing concepts of operation. So seeing whether that slew to queue works, seeing whether the different assets or different platforms that you're bringing on board do provide value. So that's much easier and cheaper and quicker to test in a simulated environment. And then ultimately, again, you will go to the real world, but this provides a foundation for guiding those real world exercises. So given your better understanding of your stack's capabilities and where it's weak, you can then go out and collect much better data, collect much more targeted field exercises. The last thing here that I'll mention is, the synthetic data sets can provide a really powerful way of augmenting training data sets, especially given the rarity of certain asset classes, given some of the adversaries we expect to face. Synthetic data can help make those models a lot more accurate. So I know I'm at time here. I do just want to kind of cap this off with a real world example of Task Force 59. So they headed out to IMX in February in Bahrain, but weather prevented them from doing a lot of the testing that they wanted. So it really shortened their window for real world testing. If they had used a simulation based tool, they could have seen how the integration would have done. They could have actually done a lot more of that testing ahead of time, and then again, that real world testing could have been much more targeted. So I know I'm at time here. Thanks everyone for the time, and hope to talk soon.
Yep. Thank you, Ezra, for that presentation. Thank you, everyone in the audience, for tuning in. We're going to go ahead and take about a 3-minute break, and then we will go on to the next presentation. But thank you again, Ezra.